This video is about functions and graphs. The objectives. First of all, we will learn how to distinguish between a relation and a function. Second objective, find whether an equation represents a function. Find whether a graph represents a function. Evaluate the value of a function at a certain point. Graph a function. Find the domain and range of a function using a set builder. And then find the domain and range using interval notation. Go ahead and take a look at the characteristics of a function. A function relates a pair of values x and y as follows. It receives as input one of the values of x, and the values of x are coming from a collection of objects called the function's domain. The function's independent variable is x. That means x is independent variable, so by default y will be the dependent variable because there is a relationship between x and y. The function's domain object are usually members of the set of the real numbers, but not all the time, but usually. Here is a modeling of the function in terms of the input, process, output model. The input is represented by x, the variable, which takes values from the domain. The domain is a set of real numbers. Usually, the function will map members of the domain to members of the range. We'll talk about the range in a minute. But f of x is a definition of y. It represents y. And that's why we see the relationship between x and y. So the input is x, the output is y. The function assigns each domain member, which is a value of x, to a single member of its range, which is a value of y, which is equal to f of x, as we said. The function's range is also a collection of objects that can also be members of the set of real numbers. The function may assign more than one element from the domain to the same element in the range. A function cannot assign a single element in the domain to more than one element in the range. The mapping must involve every element in the domain. However, the mapping may involve all or some of the elements in the range. The number of elements in the domain of a function can be same or different than the number of elements in the range. Let's go ahead and check one of the characteristics. In particular, we want to check the characteristics that states a function cannot assign a single element in its domain to more than one element in its range. Let's check the following equations to see if there are functions. Of course, if there are functions, then they will assign a single element in their domain to a single element in their range, not more than that. So to do so, that is, we want to check the functions. To do so, we rearrange the equations by symbolically expressing y as a function of x as follows: y equal to f of x. Equation number 1, 2x plus y equal to 6. For this equation, we're going to say f of x equal to 6 minus 2x. All what we did is we moved 2x to the right hand side and we replaced y by f of x. So this is what will result: f of x equal to 6 minus 2x. Now, we need to show that f of x is different for different values of x. The table below shows selected values of x on the first row and their corresponding f of x on the second. Let us evaluate f of x for values of x ranging from -4 to +4. So we'll just take -4, -3, -2, -1, 0, 1, 2, 3, 4. So this is the first row, and this is the values of x, and this is the second row, and this is the values of y. We can see that when x is equal to -4, y is equal to 14. So if we put -4 over here, that's going to be equal to 6 minus 2 times -4 will give us 6 minus 8, which is 6 plus 8, and that's equal to 14. And so on. We can just take an example. When x equal to 0, then I will have f of 0 equal to 6 minus 0, which is 6. So, and so on. What we see over here is that when x increases by 1, going from one cell to the one to the right, x increases by 1 in the first row, if we go that way. But then we also realize that when x increases by 1, y decreases by 2. So that's the ratio. And this is a linear relationship. So without loss of generality, the table shows that when x increases by 1, f of x will decrease by 2. Therefore, f of x equal to y is a function because different values of x are mapped to different values of y. Let's take a look at example number 2. X squared plus y squared equal to 1. Then we can solve this equation by saying y equal to plus or minus the square root of 1 minus x squared. Since solving for y gives us y equal to plus the square root of 1 minus x squared, and y also equals to negative of square root of 1 minus x squared. Since y has two values for the same x, then it's not a function. It follows that y in equation 2 is not a function due to the fact that every value of x is mapped to two values of y, except for x equal to 1 or x equal to -1. So this is not really a function. Between, or the difference between a function and a relation. Unlike a function, a relation can map any element in its domain to more than one element in its range. We're going to go ahead and answer the question, what is function notation? We use a special notation f of x, which reads as f of x and represents the value of the function at the given value of x. For instance, f of x equal to x squared minus 2x plus 1. If we are interested in finding f of 3, then we plug in 3 instead of x to find the value at 3. So we plug in 3 here instead of x. We'll plug in 3, and that's what we'll get. So f of 3 is equal to 3 squared, which is 9, minus 2 times 3, which is 6, plus 1. So if we add up, we'll see 9 minus 6 equal to 3 plus 1 equal to 4. How do we evaluate a function? For the function f of x equal to x squared plus 3x plus 5, evaluate each of the following. Number 1, f of 2. Number 2, f of x plus 3, and then f of negative x. All we have to do is we have to plug in instead of x 2 here, and then over here 2 squared plus 3 times 2 plus 5, and over here we just replace x by x plus 3, and over here x plus 3 all square plus 3 multiplied by x plus 3, and over here we just change the signs. So it will be f of negative x equal to x squared is going to remain the same. Over here it will be negative 3x. Let's take a look at plugging 2 over here. The A, example A, or question number A. So f of 2, replace x by 2 in the equation, then perform the mathematical operations to find the numerical value of f of 2. Then we will repeat the same step on B and C to answer the question. Okay, we're going to go ahead and look at graphs of linear functions. Linear functions are the straight lines. The graph of a function is the graph of the ordered pairs. To graph a function, you need to know its y-intercept and its x-intercept. By y-intercept, we mean where the graph crosses the y-axis, and by x-intercept, we mean where the graph crosses the x-axis. Now let's take a look at this. Find the y-intercept by evaluating f of 0, because 0, f of 0 is where the graph crosses the y-axis. Find the x-intercept by setting f of x equal to 0 and then solving for x. This step implies the coordinate for x is the x-intercept and the coordinate for y is 0. And this particular point is where the graph crosses the x-axis. Knowing 2 points, the first point is 0, f of 0. The second point is the x-intercept, 0. Knowing 2 points is sufficient for graphing of a linear function, since the linear function is a straight line. Go ahead and graph linear functions. Exercise how to graph linear functions. To do so, we're going to start with 2 simple questions. Question A is graph g of x equal to 2x. Question B is graph f of x equal to x plus 1. We're going to leave question A as an exercise and we'll be graphing question B, which says f of x equal to x plus 1. To do so, we have to use the steps on the previous slides. For your convenience, we're going to provide the steps one at a time. Step number 1 says find the y-intercept by evaluating f of 0, because the 0 coordinate, the x coordinate, which is 0, and the y coordinate, which is f of x, is those of the point where the graph crosses the y-axis. So f of x equal to x plus 1 implies f of 0 equal to 1. Just plug in x wherever x is, plug in 0. That will give us f of 0 equal to 1. And f of 0 equal to 1 implies that the y-intercept is at the point 0, 1. That is, the graph will cross the y-axis at the point 0, 1. The second step is to find the x-intercept by setting f of x equal to 0 and then solving for x. This step implies that the x-intercept is the x coordinate and the y coordinate, corresponding y coordinate is 0. These two are the coordinates of the point where the graph crosses the x-axis. Let's apply this step. So f of x equal to x plus 1, we're going to set f of x equal to 0. So we will have 0 equal to x plus 1. which is 0 equal to x plus 1, then we'll solve for x, and by doing so the x-intercept is -1. Hence the graph crosses the x-axis at the point -1, 0. The graph for fx equal to x plus 1 will appear next. Here is the graph. We can see that the x-intercept is -1 and the y-intercept is 1, and this is the graph straight line. To determine whether a graph represents a function or not, we use what is known as the vertical line test, and we will be talking about this quite a bit in the next lecture. But for now, the vertical line test for the functions, we're going to just look at the definition. If any vertical line intercepts a graph in more than one point, then the graph does not define y as a function of x. Let's just take a look at two examples. This is a graph of a circle. If we draw a vertical line anywhere going into the circuit and getting out, it will be crossing the circuit in 2 points. So the circuit graph is not a graph for a function. Therefore, the equation of the circuit is not an equation of a function. Let's take a look at this graph. We can see that no matter where we draw the vertical line, we will not find anywhere where the vertical line crosses the function in red here in more than 1 point. So this is the graph of a function. Which of the following graphs is a function? And then the graph on the right hand side is the function. Practice. Use the vertical line test to identify graphs in which y is a function of x. Obviously, over here we don't have a vertical line, but we have the y-axis. The y-axis is a vertical line. So we can say that for x equal to 0, the graph has two values. It has a value over here, the value over here, so it violates the vertical line test. This graph does not violate the vertical line test because it crosses the y-axis at 1 point only. This is also a function because the vertical line, in this case the y-axis, crosses the graph at 1 point. This is not a graph because if we draw a vertical line, we will be crossing the graph in 2 points. We're going to go ahead and summarize by answering some of the questions. The first question is, what is a relation? A relation is a set of ordered pairs. What is a function? A function is a relation, but there is one restriction. The restriction is that every element in the domain must be mapped to an element in the range, and no element in the domain will be mapped to more than one element in the range. How can you define or determine if a relation is a function? We draw a vertical line passing through the graph of the relation. If it crosses the graph in more than 1 point, then the relation is not a function. How can you determine if an equation in x and y defines y as a function of x? We solve the equation for y. If y has more than one value, then y is not a function. Why? Because if y has more than one value for the same value of x, then we will have problem with the vertical line test. Give an example, the vertical line test. We're going to go ahead and check to see if what kind of information can we obtain from graphs of functions. To do so, let's keep in mind the following. Closed dot. Closed dots indicate the graph ends or begins at the point, and the point is part of the graph. Open dots indicate that the graph does not reach the point, and the point is not part of the graph. For example, this is a closed point, closed dot. This is open dot. Let's go ahead and give some examples. The above graph tells us the ranges for each of the top 3 grades. So let's take a look at. Assume that this is a graph, and assume that the x-axis shows the total for an exam. So between 70 to 80 deserves a grade of C. Between 70 to 80, but 80 is not included. That's why we have the open dot. Open dot says what? The point is not included in the graph. It's not part of the graph. So we can see that this portion of the graph has a closed point here, a closed dot. That means 70 is indeed part of the grade C. But 80 is not part of the grade C. But if we go up, we can see that 80 corresponds to B, and that's why when the grade is B, we see 80 as part of the graph, and so on. 90 is not part of the B, and that's why we have vertically above 90 we have an open dot. So 90 does not deserve a grade of B, but rather 90 deserve a grade of A, and that's why we see the closed dot here. And we can see that there is no end here. That means from 90 and on. From 90 and on, this is theoretical, not practical, but from 90 and on, the value will be A, or the grade will be A for anything greater than 90. Identifying the domain and range from a function's graph. Domain. Domain is a set of points that represent the input to the graph or to the function. Domain is normally found on the x-axis. The range is set of the output. It's found on the y-axis. And identify the domain and range from the graph of a function. We can see that the graph starts at 8, and the point 8 is an endpoint. This dot, it's a closed dot, so 8 is included. So from the x-axis, the maximum value that this graph includes is 8, and the minimum value obviously is negative infinity, because this graph, according to this arrow, it's heading all the way to negative infinity. So the smallest value for x will be negative infinity. The largest value for x will be 8. So the representation is going to be in, for example, the set builder notation. If we use the set builder notation, then we're going to express the fact that the graph starts from the point 8, including the point 8, and it goes all the way until negative infinity, not including negative infinity. And that can be expressed as set of all x's such that the vertical lines means such that. So set of all x's such that x is greater than negative infinity, less than or equal to 8. Now you can tell that less than or equal in the set builder notation represents the closed dot, and greater than represents the open dot, we don't have an open dot, but it also represents a point that we cannot reach, the graph cannot reach. So using the interval notation, we could just say the domain is between negative infinity, where this is a parenthesis, then comma, the number 8, which is square bracket, not parenthesis. So the square bracket has the same role as the less than or equal. Both of them represent the closed dot. And the parenthesis has the same role as greater than, because it represents either an end of the graph that has an open dot or a point that the graph will never reach, either way. Now, what would it look like for the range using both the set builder and the interval notation? I'm going to go ahead and talk about the set builder. So to determine the range, we don't look at the x-axis, we look at the y-axis. So everything that we're going to be doing is with respect to the y-axis. So first of all, we're going to find the highest point, the point that is the most further away from the x-axis, and that point is going to be the highest value for y. So if we look at the graph, we can see that it starts somewhere here where x is close to 6, and it's concaving up, going up until it goes to the top. So the top could be where y equal to 10. The top could be where y equal to 10, and it's very clear that the graph will proceed towards infinity. So the smallest value, which the graph cannot reach, but it will be heading towards, is negative infinity. So the range, we could say that, is the set of all y's such that y greater than negative infinity and y less than or equal to 10. So let's just go ahead and write it down. We can write down the range as follows. So we can say the range in set builders equal to the set of all y's such that we said y must be greater than infinity, negative, and y should be less than or equal to 10. Obviously, this is the set builder notation. In normal notation or interval notation, we could just say that y, or put the negative infinity, comma 10, but then for the y, open from this side, and from this side it's closed. You could go ahead and let's go ahead and try to identify the domain and range of a function from its graph. This function is really messy. Let's see the question. It says use set builder notation to identify the domain and the range. This is like an exercise for you, but I'm going to go ahead and identify every segment of the domain. Let's start with this segment. This segment starts at negative infinity and ends at negative 6, because 6 is not included, and infinity, obviously the arrow cannot reach it. So this is the first. The second segment over here, it starts at negative 6, has the smallest value, negative 6, and then it goes to negative 4, because this is negative 4, so negative 4. None of them is included, so it's going this way. And this point, this is a singular point, a standalone point, so we'll just represent it. It is negative 6. Now we have to identify this one. This one starts at negative 4, which is not included because it's asymptotic, it's going that way, and negative 1. So negative 1 is not included also, so it's going to be this. And then this segment. This segment starts from -1, where -1 is included, so we're going to go ahead and put this, and it ends at 4 not included, so it's going to be this way. And of course we have inside 4 is included because it's a standalone point also. Finally, this is the last value, and it starts at 4 not included, so 4 parentheses, and then it ends at infinity, also parentheses. So this much we have